Okay, welcome to Module 4 in AGEC 685. We have been working on linear programming as sort of a instructional topic for optimization problems, considering its depth, but mostly with sort of small, simple examples, and we didn't do a lot of modification. So if you remember the first time we went through, we thought about solving the optimum, doing some experiments with it to try and understand the plan, and then in the last module we expanded a little bit, got a new type of model in the network model or the transportation model, and we also focused on sensitivity, the automatic reporting of some different outputs that helped us understand that solution. Now we have a new topic, still in linear programming as our basic method. But we're going to think about these problem types and think about a little more deeply, how do we make these things more real? How do we better represent real world situations? And one of the ways we'll do that is you'll read a chapter that goes through just a wealth of examples. It'll give you detailed sort of, the problem or the crux of some problem and how someone might set that up in a linear programming environment. In this module, I'll also be asking you to think about your own capstone idea, your own capstone topic area, and try to fit it. Try to think of an optimization problem that would provide insight, descriptive application. You do not have to find data and make it work, but think of a descriptive sort of linear program or optimization problem that would assist you in working towards your objectives of your research plan. Let's just think back to the start of Module 3. We talked about problem types. Really, mathematically, there's maximization and minimization. Those define which direction objective equations are searched over. Then there were the classes of problems on resource allocation, blending mix, and network models. And we can basically fit everything into one of these generic types. We would just need to be thoughtful, maybe creative in the way we construct things. And we have two areas to be creative. We can be creative in the constraints. We can be creative in the activities. Right? We have those two choices. And at this point, I should note, in the classes of problems, it's very common to see dynamic versus static split apart. Static models, if you don't know, are one shot or a single period of planning, right? There could be stages, but the idea is you run through an entire production or planning cycle and then come up with the plan and do analysis. And the key sort of feature of those is once you've got the plan for the system, you don't have an impact or a carryover effect into future decisions. Whenever you start, you hit the next starting point and decide anew, and they call them world end problems sometimes. The world ends with the end of my problem. There's no terminal condition that you have to meet to ensure survivability or planning. And of course, those lack some reality, but they can be important for understanding trade-offs that don't really depend on terminal conditions. And so we do a lot of static problem analysis. Dynamic models are specifically multi-period. They have specific carryover or intertemporal between planning period linkages, and that carryover sets a new set of initial conditions for the decisions in period 2. All the period 2 decisions and activities set the initial for period 3, and obviously the complexity here gets hard because you still have to come up with some terminal condition to stop that problem. And so you can end up with lots of situations, especially in a linear programming environment, where you can mimic in a one-shot static everything that you would want to get out of a dynamic model. There are some, though, that are important. If you think about, we've talked about crop programs, crop planning models, just because they're sort of the classic teaching tool. But you could think about it simply enough. Land preparation, fertilization, and harvest being sort of distinct stages in a planning period. And that fertility that's added in one period may have a carryover. A carryover equation. What is the status of the land fertility at the start of the period one, and what's the status at the end of period one? And in that way, all the decisions in the activity of period one will set a new set of starting values or a new set of initial conditions for decisions in period two. If the world ends, then fertility at the end of period one doesn't matter, because period two is not part of this. So something about a maintenance condition would let us do a static model, but a dynamic model, a true dynamic model, would say, okay, let's put together a crop planting program for 5 years. Think about how we're going to manage nutrients in the soil and fertility, and let's do it in the best way possible, spreading the costs out over these planting periods as appropriate. And so really, as a point of emphasis on something that we're not going to spend much time on, when we talk dynamics, think back to your work with Dr. Bolgi and thinking about discounting, because the key for everything in dynamics, multi-period sort of decision making, is how do you set the discount rates? How do you trade off the future versus today? Because you can game the dynamic models to give you any results you want, or not any result, but practically lots of different things become admitted as reasonable optima when you start moving around discount rates. Okay, so that gives us back into the classification and gets us sort of our intro to the Module 4 topic, and it's really the first time we're going to say, let's be modelers, let's model, and our technique is just linear programming. Till now we've been learning LP techniques using example models, but this time I want us to think more broadly about what are the sort of build-up, right? Rather than just what could I do if somebody gave me this information, how would I build this up? And we're not going to go from scratch, but we will scratch together some different pieces of models and think about how they impact our analysis. And of course, the key learning objective here is you thinking about what's the information available to me, how might I use some of these in my own work, or if I were just looking at someone else's work, something came across your desk at work, have they considered gathering more information and really teasing out this one component? So what do? Well, we example a host of problems to see how they're made to work in LP. That obviously accomplishes something for us of letting us learn the limits of the linear programming method better. And of course, any technique will have those kind of limits, and relaxing some of the limits of those techniques may allow even more problems in. So later in the term, we will look at relaxations, but we'll be able to understand why quadratic programming or risk preferences need to be dealt with in a different environment than linear programming. And we'll deal with integer constraints. So thinking about a choice on plant location. Well, you cannot put 2/3 of a plant in one spot and 1/3 in another spot. And so there are going to be some problems where we just have to force in integers, and we'll talk about that later. So you'll see the scope and where we hit those limits. I hate the word tricks, but it seems like all the textbooks use it, and so we'll look at the tricks, or what I would call standard tools, of getting details into linear programming models to admit specific kind of interactions or specific implementations that may be useful. As I mentioned already, we only have two things at our disposal, really, those being activities and the way we define them, and constraints. And then of course I want to think about data. So as we look at an example model, I'm going to give you sort of a set of budget data or some basic data, and think about how we might go back to the drawing board and reclassify activities or reclassify constraints to deal with the problem a little better, see how the solution changes, and see how our analysis and the questions that we're now admitted or now have the ability to discuss change as we do that. Okay, everything comes at a cost. modeling too, and more detail comes at a cost. And so we always want to be thinking about what are the analytical or the sort of discovery advantages versus the cost of getting things in. The data and information is always a big one for us. So you learn these techniques with very simple models since you understand the trade-offs, but in fact most models consist of either blocks or segments or layers of multiple types of linear programming, of the sort of toy models that we've been learning in class, or the practice models, examples. And so if we could think about linking some of those up, we could think about improving representation, improving our modeling, and maybe one of the ways we could think about that is examine the information data sources and being intentional about how we incorporate assumptions. So with that, let's talk through something that I'm recording this in 2018, and so I've talked to you about this if you're part of the 2018 class. If for some reason this is later than 2018 and I didn't talk about this, I will just remind everyone what's going on here. There's this book, it's called How Not to Be Wrong, and one of the chapters really is just to focus on sort of linearity and projections and what qualifies as analysis. The book's by Ellenberg, and he basically asks the question, when will the whole country be obese? And so there's these published estimates that talk about how is the percentage of the population that qualifies as obese or overweight growing, and they take that number, or these measures, and these are little cutesy drawings from his book, and they plot out a few of those, and they say, well, let's just project off of that, and eventually everyone's going to be obese. So how long would it take? And so the first issue that Ellenberg sort of takes issue with is putting a straight line projection through these data points is troubling, because one, it looks like there could be some slight curve, and two, the nature of populations, as more and more people get converted over from type A to type B, or in this case from not in the category to in the category of overweight or obese, you expect everything to slow down, because there are certain people who are close to the point of being moved over to that category, and others are quite far, and you would expect the length of time to get longer and longer and longer to move additional people over. So using linearity is a problem, and just like if you have any sort of theory training in populations, demography, biology, we tend to think of things as sort of logistic, right? So there's some sort of easy or fast-moving group, and then things this is sort of the fast initial rate change, and then the rates start to slow. You get what we would call, I guess, an inflection point here, where the curvature changes and it gets flat, and it takes a long time for this sort of sigmoid type behavior. We see it in all kinds of things, all kinds of biology. So thinking about yield and projecting yield, linear trends say that things increase without bound. So if we're talking about a crop yield, but people that study these things and study them in depth think, well, let's think about the details of what's causing yield to grow, right? Is it that there's some new technique for growing crop, and it's an improvement, right? It's a more productive technique. And so really what's in play there is how fast is it being adopted in the population. And so if it really does have sort of a plateau or a maximum yield, then we would expect as the adoption becomes closer to 100%, the trend growth in yield would start to slow. And so a linear trend wouldn't be appropriate, but a logistic trend would, right? And so that's one possibility. The other problem with the linearity is if you keep growing this thing the way they've done it in this chapter, drawing a straight line through here and saying we're projecting when the growth in the obesity population as a percentage, well, once it hits 100% in 2048, everyone is obese. But this linear trend doesn't stop, and so mathematically, with that kind of function, there's no problem saying after the year 2048, our prediction is now that the overweight/obese population is beyond 100%, and that has no meaningful interpretation. So at a minimum, something that fits through here that respects the fact that this thing has to bend as it gets closer would be needed. But there's a bigger problem, right? And this is the thing we talked about again in 2018 in August, the internal inconsistency. The authors use a population average, but they also compare different subgroups of the population. So they say that some groups have different rates, and that means they'll have different dates when they get to the benchmark of 100% overweight obese. So as constructed, 2048 is 100% of the total population, but many subgroups don't hit that 100% obese category until later because their subgroup has a slower rate than the population in general. Well, that's a huge projection problem since it basically denies the 2048 number as being legitimate, right? It's internally inconsistent. There's no truth to the fact that 100% of the population will be overweight obese category in 2048 when you're telling me there's another group of the population that's part of the total population that it doesn't happen to until 2051. So I went back, I read the journal article just to be clear on all this. They say their true purpose is to give an index measure. So we want people to understand sort of the severity of this, and the easiest way to do it is to give this date, this changeover date when we will hit 100%. Well, that's fine, but that kind of simplicity comes at a cost. And if you simplify your way into an internal inconsistency, that's just too high a cost. So we want to ask the question, can we do better? Can I do better? I'm not asking you to replicate this. Can we do better than what they've done, but still simple, but avoid the internal inconsistency? And if you want to sort of flashpoint the internal inconsistency, it's right here. So this is their source article, Table 2. Excuse me. It says 2048, everybody is in the category overweight obese. The men in the group, not till 2051. The women, 2044. So what's happening here is the 2048 is sort of the midpoint of the average based on the percentages, but that's not how averages work, right? That's not how time proceeds. You can't say everyone in 2048 except not some, because now you've just defined 100% to be something different than what it exists as in the real world. So I went back one table before and found their actual projection estimate. So it turns out they have men and women by three demographic groups, non-Hispanic, white, black, and then Mexican American. And they estimated different rates for each of these. So this is the rate of growth, and this is the current percentage, the starting value of the percentage of that population that falls in the OW obese category. And so these are in percentage terms, and I don't like that. So I wanted to get rid of it, so I went and found some population data from 2000, first for males, 20 to much older. I found the population data, and I found enough information that I could construct white, black, and a Latino category to use as benchmarks. I did it for male, I did it for female, and I built this spreadsheet. And what I want to do is convert their percentage intercept value to a total population number, and then I want to convert their percentage rate into an actual slope that I can use in terms of this increment. And so what I want to do then is take this obese and overweight population number, and then I'm going to increment it every year by this quantity. And I'm going to do it for every subgroup individually. So I've got non-Hispanic white, non-Hispanic black, and Mexican American, which I'm proxying for with the Latino estimates of the population. And I've got 3 categories for male and 3 categories for female. I'm going to project all these individually because they have estimates, right, that respond individually to these. And that's where their internal inconsistency is coming from. They have 6 discrete estimates that respond or look at individually the population groups, but then they have an average estimate, which is somewhere in the middle of all of these, right? And so you can't do a projection off of the average without recognizing that you can't use it. You can no longer use it for total, right? It's no longer representative when you're trying to work towards some total measure. And so what I'm going to do is do the 6-group projection individually, and the spreadsheet's available for you. I guess let me open it for you so you can see. Okay, this spreadsheet's provided to you without warranty. I did take all that population data and converted it here. But I did it quick, and I just wanted to get some numbers together, so I put together the population assumptions to convert to quantities, to actual population numbers, not percentages. And then I took their estimates, these are their estimates, and I converted those based on the total population in each category to some quantity-based projection numbers. So 50.76 is the starting value, each year incremented by 0.33. And then you'll see down here I went through all of the years. Okay, so 2004 to 2150. And what we do is we just count up the total. So count across here, this is the population in each group, these are the contributions to a total, and then we can just plot that. And just to get ahead of myself here, when we plot this total, we end up with a linear segmented graph. So a bunch of growth in the population when everybody's still there, but what happens is eventually, I can't quite tell, eventually one group, the entire group becomes obese, and they fall out of the new projection, right? Because everybody there has been converted to the category OW, obese. And so you end up with a new linear segment. And then here it's much more distinctive. Another group falls out, and you get a flatter line because the people who have yet to be converted have the slowest rates of conversion to not obese to the obese category. Okay, and so that's what's going on here. And so I think next will be my graph, and so we end up with this sort of linear segmented thing that approaches much more that logistic or sigmoid type graph. And even more importantly, we got rid of the internal inconsistency. Now it is impossible for us to claim that 100% of the population is currently obese, but there's one group in the population who is not 100% obese. Okay? And so that's what we were working on. How good is our projection? If we finish, we shouldn't just say, we fixed everything. We should say, should we still be fixing some things? And I still have my suspicion that I don't have a great measure. One, I don't know how good their estimates were, but that's okay. We could think about that later. The glaring item is I'm really not projecting the actual population percentage. I'm as in the current population, because one thing we know is every day new people enter into my 20-year-old group, and I'm not accounting for them at all. I'm not accounting for the fact that as time moves forward, we are sort of resetting the denominator as the total population. And so my measure is really just as of this day in whatever year, 2004, there were this many people in the population. How long before all of them, the ones that were classified as 20 years old by their subgroup on that day, how long before they all become obese or overweight? And that's what these numbers represent. When really what you're interested in is the population, because new people moving in may be the ones whose behavior are the most affected. They may have much lower rates, and they would be lowering the entire group rate of this conversion process, and may provide a very different dynamic, a very different projection. We may see a reversal of trends just by the growth in the population and how their behavior differs from people who were categorized as 20 years or older previously, right? So the younger generation moving in may have a huge impact here, and we're missing that completely. That would be a much more complicated model, and to be honest, it's probably why the authors chose their approach back here to do this in percentage terms. If you do this in percentage terms of the population, right? So their current version 67.5, how is it changing over time? They're measuring two things at once, the obesity population and the total population. So they're getting both growth rates at the same time, but if you convert to quantity, you have to set an initial point in time and deal with the different growth rates separately. So they're trying to project this way, and it turns into, I think we can make a good case, a big mess for saying anything other than the problem is serious. And if you want to know how you can simplify something and try to make a serious problem put into a conventional sort of metric, or this is the year when everyone is obese, and make a bigger problem for the analyst, then you just have to read Ellenberg's chapter and see how he kind of mocks this. But You can find the problems all over the place just thinking about climate change. People go out, they estimate good, valuable information on how the climate's adjusting. It's the projections that always get tricky, and policymakers want them. But you might ask yourself, do policymakers want them because they are going to find all kinds of issues that occur with the fact that the farther out you project something, the less we know, right? The more moving parts that have to be accounted for, and that's always an issue. And so we need context, and projections are certainly a good way to find context. They also require a lot more detail, a lot more care. That's not really our topic in this class, but we have a similar issue that we might think about. How does it relate to linear programming? How does this linearity problem that we just saw there, and thinking about rates and getting the rates right, how might it show up for us? Well, let's consider again, our crop type problems are really any productive activity where the output per unit input could be an important measure. Take crop X, 1 acre of activity returns $1 net return Y. That's implicit inside of that activity return here is some yield measure, some output per unit input. And we have a fixed price usually that we're saying is the assumption. And so this yield measure becomes important. Well, let's say that crop activity really in the problem is 1,200 acres and it's going to be planted to the crop. But what if really, if we learned a little more about our 1,200 acres, we found it's 300 high yielding acres, 700 average yielding acres, and 200 low quality or low yielding acres. How would that yield function look? Well, if we say that you plant the best yield first, and then the medium, and then the low, then the true yield function looks like this. Arrow 1 is the high yielding, arrow 2 is the low, the medium, and then arrow 3 is the low. And so you end up with acres planted, and the total crop that you get looks like this. So it has this nonlinear, well, the total function is nonlinear, it's linear in segments. And if you just assume the average, right, we plant all 1,200 acres, this is the total output, then this dashed line is the average yield line that takes you from there to there. And so if you assume that same yield for all 1,200 acres, we have an issue, because we know that in our crop planting problems or our allocation problems, it's about how do we allocate resources. And so a huge piece of information for us could be the fact that this crop has a much better response on the high yield acres than on the low yield acres. And so we may think about what kind of activity do we want to consider, right? Planting here versus here. If we plant all of our crop, if we max out a high yield, high value crop on the high yielding acres, is it still true that we prefer it on the medium yield acres? And we can never understand that if we use this average measure, okay? And so up till now, we've certainly been doing that. And we may find that it's appropriate to do it. But if we wanted to think about it differently, we would think about it this way. What does corn look like when we plant it on option 1, activity, a corn activity that says plant me on the high yield, option 2, plant on the medium yield, option 3, plant on low yield. And all we need is the different information on the constraints. All we need is how do these acres differentiate? How are they not homogeneous? And then we could come up with activities that think about, are there different input requirements for planting corn on a high yield versus medium yield? Does it require different fertility, land preparation, hours of work? What other things? And you could think about having a much more detailed model that gives you much more sort of insight into the planning process, right? And where we see this a lot is we find out some farmer has a planting mix that we don't understand because the return is better for a crop that they're growing on a minimal amount of acreage. Well, if you actually knew the farm and went out and collected all the information, you might find that the farmer is doing exactly the right thing. They may have a limited amount of high return, high yield acres that can support the activity with the highest return. And so they may be doing a very optimal situation if we had just investigated it further. There's additional options, ... So 4 and on, you could think about other activity definitions. Corn that follows corn, corn that follows soybeans, corn that follows wheat. Rotation crops are a big piece of linear programming. So a mixing of activities. How am I going to allocate a single resource between sort of half corn, half soybeans? It gets us into sort of a dynamic or a sequence type of event that's a little bit different, but it may have different yield potentials, right, or different productivity potentials. So we're still talking about a homogeneous product. We're still talking about selling corn as the product, right, of the same quality that draws the same per unit price. But we're talking about a bunch of different activities, different ways of producing it that says it will draw on our resources in different ways and may be very important for us as planners. With that, that's sort of our introductory lecture. Went a little long, but I wanted to sort of set things up before we get into some of these demonstrations and talking about different techniques and sort of, again, tricks that we'll use. And if you wanted to read more on the obesity thing, sort of tricks, I do have a scan of this chapter, and you can look at all the data that's there. But I wanted to reference all that since I am kind of presenting it as a counter piece of analysis, so that you should have the ability to check me if you want. With that, I'm going to close out, and we will have a short quiz after this lecture.